Hello everyone. So as usual, go to the polls tab and let me know which problem you would like to discuss today. Okay, the first requested problem is problem 53, and actually interestingly, this was the exact same problem was done during the lecture. This is about the NGF of random variable with mean 1. So if I go to the lecture, okay, so here it is. So there I did a computation of moment generating function of exponential random variable, which is this one. This is example 2. So if x follows exponential lambda, the PDF is lambda times e to the power negative lambda x. In problem 53, it has PDF 1 times e to the power negative 1x, which means it is exponential 1. So essentially, you need to repeat the calculation from example 2 with lambda is equal to 1, and the answer would be 1 over 1 minus t. If you replace the lambda by 1, you would get 1 over 1 minus t. Um, the computation of lambda, and repeat the exact same computation. Lambda is equal to 1. And the answer should be, so the NGF of x, in this case, okay, if x is equal to e to the power negative x, when x is positive, and NGF is going to be so if you do the computation, which is expectation of e to the power tx, that is integration 0 to infinity e to the power tx times the PDF, which is e to the power negative x dx. This will be 1 over 1 minus t if t is strictly less than 1. And then the problem asks you to check your answer for the mean and mean by direct computation, etc. So expectation of x from NGF is going to be 5 prime at 0. You can do the derivative and see that this is going to be 1. And expectation of x square, which is the second derivative of NGF evaluated at 0. You can do the calculation, you'll see the answer is going to be 2. So essentially we need to differentiate this function with respect to t once and plug in t equal to 0, you will get 1. Differentiate twice, plug in t equal to 0, you will see 2. The exact same thing was done during the lecture, so I'm not repeating the calculation again. And the direct calculation, so okay, by the way, So this would imply that the variance of x is going to be 2 minus 1 square, which is 1. And if you do the direct calculation, then you would see that expectation of x is going to be integration of x against the PDF, which is e to the power negative x dx. Again, this integration was done several times. You would see that this is going to be 1, and expectation of x square, if you do the direct calculation, is equal to infinity x square e to the power negative x dx. You would see that this integration is going to be 2. Alright, so that's all about problem 53. Let me see if you have requested problem 53 and if you have any question about this. Otherwise, I will move to the next requested problem, which is problem 54. Okay, so the next requested problem is problem 54. This is about, so let me see what the problem is. Okay, so you are given a PDF and you want to compute its NGF and the moments. Okay, so the PDF is excuse me. Okay, the PDF is given by fx is equal to 1 when 0 less than x less than 1. Okay, so which is essentially this is essentially uniform distribution in the interval 0 1. If you recall uniform distribution, the uniform distributions had PDF 1 over b minus a. So if your a and b are 0 and 1, the PDF is going to be 1 over 1 minus 0, which is simply 1. When x is between a and b, that is x is in 0 and 1. Anyway, that's not relevant for this problem. We want to compute expectation of x to the power n and NGF. Okay, so let's first do the NGF, which is phi xt. By definition, this is expectation of e to the power tx, that is integration 0 to 1 e to the power tx times PDF, which is 1 dx. And if you do the integration, this integration with respect to x, so t is acting like a constant, and you see that this is going to be 1 over t to the power tx. And if you plug in the bounds, it's going to look like, so 1 over t to the power tx, and if I plug in the bound x is equal to 1 to 0, so I see e to the power t minus e to the power 0, which is 1. So the MGF looks like 1 over t e to the power t minus 1. And okay, and the moments, right? So we differentiate this to get the moments. So by the way, let me rewrite this. So MGF, which is phi xt, that is 1 over t times e to the power t minus 1. That can be written as 1 over t e to the power t minus 1. The expansion of e to the power t has 1 plus t plus t square over 2. That 1 and 1 will cancel. So you will get t plus t square over factorial 2 plus t cube over factorial 3 plus 2 to the power 4 over factorial 4, so on. And if you adjust by this t, it's going to look like 1 plus t over 2 factorial plus t square over 3 factorial plus t cube over 4 factorial, and so on. So this is the MGF of this random variable. If I write it in the summation notation, this is going to look like summation t to the power, how do I write this, t to the power k minus 1 divided by k plus 1 factorial. No, sorry, divided by k factorial. Right, and k is running from 1 to infinity. So let's see, if you plug in k is equal to 1, you see t to the power 0 over 0 factorial, which is 1. And if you plug in k equal to 2, you see t over 2 factorial, okay, that's the second term. For k is equal to 3, you see t square over 3 factorial. K is equal to 4, you see t cube over 4 factorial. Okay, so that's fine. Now, to find the moments, okay, so we know that expectation of x to the power n is the nth derivative of this MGFs. Nth derivative of MGF evaluated at t equal to 0. Okay, so let's try to figure out the derivatives. So first derivative, what is the first derivative? First derivative of this MGF. So if you differentiate this function 1 plus t over 2 factorial, t square over 3 factorial, and so on, it's very easy differentiation. You see that 1 over 2 factorial plus 2t over 3 factorial plus 3t square over 4 factorial, and so on. If you plug in t equal to 0, you would see let's see, so expectation of x is going to be the derivative at t equal to 0. So when you plug in t is equal to 0, this whole part is going to be 0, and as a result you would see 1 over 2. Okay, so this is the one which will survive. Let's do the second one and we'll see the pattern. So 5 double prime t, if you differentiate it twice, okay, so if you differentiate this twice, you will see that this is going to be, so this 1 over 2 factorial will be 0, and this will be 2 over 3 factorial plus 3 times 2 times 2 times t over 4 factorial plus the next term, which I did not write this, but it should look like say 4 times 3 times t square over 5 factorial, and so on. Once again, if you plug in t equal to 0, you will see that expectation of x square is going to be 5 double prime at 0. So when you plug in t equal to 0, this whole thing will vanish, and you will see 2 over 3 factorial. So 2 over 3 factorial is simply 1 over 3. Okay. So expectation x is 1 over 2, expectation x square is 1 over 3. Let's see one more. So differentiate it once more. 5 triple prime t. So if you differentiate this thing once more, so 2 over 3 factorial will vanish. You will see that 3 times 2 over 4 factorial. So 3 times 2 times 1 over 4 factorial plus 4 times 3 times 2 t over 5 factorial and so on. Okay. And now if you plug in t equal to 0, this term will vanish, and then you will see that expectation of x cube is going to be 3 factorial over 4 factorial, which is 1/4. So expectation x cube is 1/4. Now if you are following the pattern, you see that expectation x is 1/2, expectation x square is 2 over 3 factorial, which is 1/3. Expectation x cube is 3 factorial over 4 factorial, which is 1/4. And you can guess that if you follow the pattern, that expectation of x to the power n will be n factorial divided by n plus 1 factorial. Okay, if you see the pattern, that x cube is 3 factorial over 4 factorial, x square is 2 factorial over 3 factorial, x is 1 factorial over 2 factorial, and things like that. So n factorial over n plus 1 factorial is 1 over n plus 1. Okay, so this should be the answer for expectation x to the power n. That's the first part of the problem. So what we did here, we computed the MGF, which is this one in this rainbow color, and then we kept differentiating this and evaluating at t equal to 0 to get the moments. So is this problem clear up to now? Then I will move to the second part of the problem. I'm not sure if I am audible and visible. Is my screen visible at all?
Yes, it is visible.
Okay. All right. So the first part was finding the MGF, and you keep differentiating. This is simply high school calculus, and you will find the expectations. Second part is by the direct calculation. Okay. So direct calculation. What do you mean by direct calculation? You can calculate the moments without even using the MGF, which is by definition expectation of x to the power n is going to be integration of x to the power n against the PDF, right? So fx dx. This is the definition of any expectation for that matter, and so fx is simply 1. So this is going to be integration 0 to 1 x to the power n times 1 dx, right? If you remember that PDF was simply 1, so what's that? Yeah, so here at the beginning, PDF was fx is equal to 1 from when x is from 0 to 1. So this is what I am using here. I want to calculate expectation x to the power n, which is x to the power n times 1 times dx from 0 to 1. And if you do the integration, it's very easy integration. And x to the power n over n plus 1, plug in the limits, you will see 1 over n plus 1. So which is same as from that MGF moment. Okay, so let me see if anyone is having any question about this problem. If not, I'll move to the next requested problem, which is, so I have done 53, 54. And then the next requested one is 48. Okay. So let me try to do 48 then. Okay, so what is this problem about? Prove 4.7.5 using mathematical induction. So what is 4.7.5? Okay, it is some relationship about the covariance. So it says that 4.7.5, right? So let me see. Where is that? Okay.
Sir, where is the
Yes.
question? I didn't found that one.
Problem 48.
Yes, sir.
No, problem 48 is referring to an equation in the chapter. Okay.
But sir, where is the equation? Could you please tell me the page number of that question of the equation?
I see. So the equation is listed on the page number. What is the page number? 122. Okay. So this is about. Let me write this down. This problem asks you to prove the equation 4.7.5 is listed on page 122. So let me tell you what the equation is. The equation is it says to prove that covariance of, excuse me. Okay, so it asks you to prove covariance of summation xi I is equal to 1 to n y is equal to summation I is equal to 1 to n covariance of xi y, and using induction. Okay, so I think you know the mathematical induction. It was probably in your high school. Okay, so how do you prove this? For n is equal to 1, this is fine. Just covariance of x1 y is same as covariance x1 y. So this step is n is equal to 2. For n is equal to 2, covariance of, essentially we want to prove that covariance of x1 x2 with y is equal to covariance of x1 y plus covariance of x2 y. Once again, if you follow the definition of covariance, this will follow immediately. This is very elementary online proof. This properly. X2 y. Okay. So how do I prove this? Covariance of x1 plus x2 y is equal to expectation of, by the definition of covariance, x1 plus x2 y minus expectation of x1 plus x2 times expectation of y, which is again very high school algebra here. So expectation of x1 y plus x2 y minus expectation of x1 plus x2. You know that you can write this as you can split the expectation. You don't need independence. Expectation of x1 plus expectation of x2, and you have expectation of y outside. Okay. And now you can also split this expectation. You can write this as expectation of x1 y plus expectation of x2 y minus expectation x1 times expectation y, so expectation of x1 times expectation of y minus expectation of x2 times expectation of y. Okay. So this is a very elementary algebra and fun to do calculation kind of thing. Now if you put the appropriate terms together, you see that if I put this term expectation x1 y minus expectation x1 times expectation y, what do you see? You see that this is going to be exactly covariance of x1 y plus the other term expectation x2 y minus expectation x2 times expectation y, which is covariance of x2 y. So is the basis step clear that for n is equal to 2, which is covariance of x1 plus x2 y is covariance x1 y plus covariance x2 y. Whoever was requesting this problem, so can any one of you respond if this step is clear to you?
Yes, sir.
Okay. And then which problem am I doing? Problem 48. Okay. Now induction step, right? So induction step is that you assume that this is true for n is equal to for n minus 1. So let's say covariance of summation xi I is equal to 1 to n minus 1 y is equal to summation covariance of xi y I is equal to n minus 1. Okay, suppose we have this, we need to prove it for n, right? So then covariance of, so then for n, covariance of summation xi y I is equal to 1 to n can be written as covariance of xn plus summation. These are very standard tricks, you know. So 1 to n minus 1, very standard tricks of induction. And now you see that these are two terms, xn and this summation of I is equal to n minus 1 xi, right? You can apply this n is equal to 2 basis step technique, right? To conclude that this is going to be covariance of xn y plus covariance of summation xi I is equal to 1 to n minus 1 y. Now from the induction hypothesis, you can write the expansion of this, which is covariance of xn y plus summation I is equal to 1 to n minus 1 covariance of xi y. Okay, this is from the induction hypothesis here, that when I is from 1 to n minus 1, we have this expansion. And if you merge these two sum together, you will see the desired sum, which is covariance of xi y I is equal to 1 to n. Okay, so that's it. So covariance of summation xi y is same as summation I is equal to 1 to n covariance of xi y. Let me know if you have any question about the whole process. So this was problem 48, and what is the next requested problem? 54. Did I do 54? Okay. 43. Okay, 54 is done, 53 is done, and then you have 52, and 48 is done, 42. Okay, so let me do 52, which has 11 votes. Okay. 52 is again about the covariance. Okay, and actually 52 depends on this problem 48. So let me do problem 52. Problem 48, which I have just done now. So this problem tells you that excuse me. This problem tells you that x1 and x2 have the same probability distribution. That is same PDF for PMF, right? They are discrete, same PMF. If they are continuous, then same PDF. Okay. And we want to prove that covariance of x1 minus x2, x1 plus x2 is equal to 0. Notice that independence is not being assumed, right? So we do not need to be independent. Okay. How do we prove this? The answer is actually very simple, and it follows the same technique as the previous problem. So covariance of x1 minus x2 and then x1 plus x2, right? Okay. This can be written from the previous problem as covariance of x1 comma x1 plus x2 plus covariance of negative x2 comma x1 plus x2, right? Because what have you seen in this previous problem? It says that covariance of summation xi comma y is same as summation of covariance xi y. So I have x1 plus a negative x2. So x1 minus x2 can be thought of as x1 plus negative x2, and comma x1 plus x2 can be thought of as y. So covariance of that is going to be x1 comma x1 plus x2, which is y. So you can think of this thing as y in the previous problem. So x1 comma y plus covariance of negative x2 comma y. This is going to be covariance of x1 x1 plus x2, and this negative of covariance of negative x2 will come out as negative of covariance of x2 comma x1 plus x2. Once again, these are very similar. Like if you are wondering why this negative is coming out as negative, the fact is that covariance of, this was problem 47, I guess, covariance of ax comma y is a times covariance of x comma y. Okay, so in particular, if a is negative 1, then covariance of negative x comma y is equal to negative of covariance x comma y. The proof of these things are extremely simple and very elementary algebra. If you follow, if you have understood this proof of 48, essentially the same thing. We apply the definition of covariance, you will get the answer. Okay, and now again I expand this. So x1 comma x1 plus x2. So this is going to be covariance of x1 comma x1 plus covariance of x1 comma x2. If you are wondering how am I getting this, this is actually from problem 48. Not exactly, kind of from problem 48. So covariance of x2 comma x1 minus covariance of x2 comma x2. Okay, so I split this part like this and split this part like that. Now if you're wondering how am I doing this, so this is x1 comma x1 plus h2. You have sum on the second part, but I'm also splitting out the second part. If you look at problem 48 had the sum on the first part only. Covariance of summation xi is equal to summation xi comma y is covariance of summation of covariance xi y. In fact, if you follow the same technique, you can prove that covariance of y comma summation xi is equal to 1 to n. If you have summation in the second component, no problem, you will have the same answer. So covariance of y comma xi and you take the sum. Okay, the proof is exactly the same. So if you follow the same technique, so because of that I am splitting up the second part, which is x1 comma x1, covariance of x1 comma x2. Okay, now what I can do, I can write this covariance of x1 comma x1 as variance of x1. This was discussed during the lecture. The covariance of a random variable with itself is the variance, plus covariance of x1 comma x2 minus covariance of x2 comma x1 minus variance of x2. Okay, now what happens? Again, you can prove that there is another property of covariance. These are not properties, like these are very easy to follow exercises. That covariance of x and y is same as covariance of yx. If you switch the random variables, covariance won't change, because in both of the cases covariance of x and y is going to be expectation of xy minus expectation of x times expectation of y. If you look at covariance of yx, what you see? You'll see covariance of yx minus expectation of y times expectation of x. Same thing, right? So 2 times 3 is 3 is same as 3 times 2. So there is no difference. So covariance of xy is same as covariance of yx. Because of that, you can see that covariance of x1 x2 is same as covariance of x2 x1, and they have a negative sign that will cancel. Other part is that this variance of x1 will cancel with variance of x2. Why? Why would variance of x1 cancel with variance of x2? That is given in the description of the problem, that they have the same PMF PDF. So if you have the same PMF PDF of two random variables, they have the same expectation variance and everything, right? So here it means that variance of 1 is equal to a variance of x2 x1 x2 have the same probability mass function or density function, okay, whatever it is. Since they have the same PMF PDF, when you calculate the expectations, you will get the same answer. Anyway, the final answer is 0. That's what you are looking for. So this thing is going to be 0. This is what you are trying to prove. Right, this is what you are trying to prove. Once more, so these variances are same because they have the same PMF PDF. If you want to quickly see this, because this expectation of suppose they have, both of them are having the PDF and PMF, let's say like fx, right? So then expectation of x1, okay, hold on, let me erase this. So expectation of x1 is going to be integration of x against the PDF of x1 dx, right? Expectation of x2 is also same, right? So x PD against PDF of x2 x dx, right? But however, since if x1 if x2 are same, right, they are the same, these two integrations are going to be exactly equal to each other, right? So this should imply that, so because these two functions are same, you have like x times same function dx and x times the exact same function dx, right? This should imply that expectation of x1 is equal to expectation of x2. So they will have the same mean. Similarly, you can find that they will have same expectation of x1 square is equal to expectation of x2 square, and that would imply that the variances are the same. Okay. Does anyone have any question about this problem? Which problem was that? Problem 52. Okay, problem 48 was done, and then there was a request for problem 42. What is problem 42? I do not have that much time, so I have only 4 minutes. Let me see if I can quickly do that problem. Oh, problem 42 argued that for any random variable x, expectation x square is equal to expectation x whole square. This follows from my lecture note actually. I specifically mentioned, actually solved this one during my lecture. So problem 42. It asks you to prove that expectation of x square is bigger than or equal to expectation x whole square. Expectation x whole square. Okay, so how do you solve this problem? This actually follows from a very elementary thing which we discussed during the lecture. That the variance of any random variable is always non-negative, right? So whatever the random variable is, variance is always non-negative because we are looking at the dispersion from its mean and square. It's going to be always non-negative quantity. That would imply that the definition of variance is expectation of x square minus expectation x whole square. That is always non-negative. That's the answer. So which would imply that expectation of x square is bigger than or equal to expectation of x whole square. Okay, that's it. All right, so I think I have answered most of the problems and I'm also out of time. So in 2 minutes at 12:45, you can start taking the quiz, and the quiz is available at the usual tab, which is the assignment tab. So go to the assignment tab and you can start taking the quiz. Actually, let me change the timing then. And also in the meanwhile, if you have a question, you may ask. Okay, so I cannot change the timing now. So the quiz will start at 12:44. If you go to the assignment tab, you will find the quiz, but you won't be able to access it until 12:45. Okay, so I guess you can start taking the quiz now. have 15 minutes to complete this.